Chapter 6 is about confidence intervals for our population mean. So first, let's have a little note about simple random samples. The statistical methods that we use in this class depend on our sample data being from a simple random sample. Remember, a simple random sample means each observation or each person in the sample is equally likely to be chosen. Now, I'm not going to repeat this for everything we do for the rest of the class, but just remember it's supposed to come from a simple random sample. Because if it's a simple random sample, our observations will be independent from each other, meaning they won't affect each other. Now, there are more advanced statistical methods that will deal with other types of samples, but we won't learn how to do those in this class. Okay. So for everything in this class, just assume it's simple random samples. This is not true in the real world. You probably just want to hire a statistician. So point estimates. We can use the sample mean xbar as an estimate of our population mean mu. We call it a point estimate because our sample mean is just one number, or just one single point. So let's say we want to estimate the true population mean height mu of NBA players in 2001 to 2002. So the population mean height would be for all the NBA players. So we decide to take a sample of 10 basketball players and find their sample mean height, x bar. The sample heights I get are 79, 81, etc. up to 77 inches. The sample mean height is x bar equals 79 inches. So our estimate of the population mean height is 79 inches. So again, our sample mean height of 79 inches is our best estimate of our population mean height. So we think the population mean is probably 79 inches. But do we have any guarantee that our population mean height really is 79 inches? Well, it turns out, no, we don't. Because if I took a different sample, could I get a different sample mean height? Yes, every sample will give me a different sample mean. So we know our values change from sample to sample. That's the whole idea of the sampling distributions that we just learned about. So, for example, I took another different sample of 10 NBA players and found the heights 81, 78 up to the 75. And that sample has a mean of x bar equals 77.5 inches. So our best estimate now of the population mean height would be 77.5 inches. So how do you know which one is right? Okay, notice again here, every different sample will give us a different sample mean. That means that each sample will give us a different estimate of our population mean. And because we realize that each sample is going to be different, like, we need something a little bit better than just one number to describe our estimate of the population mean, because we know it's probably not going to be exactly right because each sample gives us a different result. So that's why instead of point estimates, we came up with confidence intervals. A confidence interval for our population mean is some kind of interval that we construct around the sample mean so that we're very sure or confident that the interval will contain the population mean. So back to our NBA example, we want to take a sample of n equals 10. Someone told us that our population standard deviation is 3.62. And we want to try and estimate mu, which is our population mean. So our sample mean is our point estimate of our unknown population mean mu. But remember, our sample mean is going to change from sample to sample. So unless we're extremely lucky, our sample mean isn't going to be exactly equal to our population mean. But it should be pretty close. Okay, again, remember, our population mean is unknown. It's fixed, it's some specific number, we just don't know what it is. Okay, so to come up with our confidence interval, let's do some review about the theory of sampling distributions. Okay. So what's our sampling distribution of x bar? Well, there's three things that come for a sampling distribution. The first one would be the shape. Well, heights are usually normally distributed, so because our original distribution is normal, our shape will also be normal. Okay, then we need to find the mean for all the possible values of x bar, and this will just be equal to our original mean, which we don't know what that is yet, so we'll just leave it as mu. Our standard deviation of x bar, though, is equal to sigma over square root of n, and we do know those. Sigma, they told us, is 3.62. Our n is 10, so this gives me 1.144. So now what does the 68, 95, 99.7 empirical rule tell us about X bar? Well, it tells us that 68% of all the possible values of X bar, I'm just going to write X bar because I can't type that, are within one standard deviation of the mean mu. So, and then it says 95% of all of our possible values of X bar are within 2 standard deviations of our mean mu. And 99.7% of all the possible values of X bar are within 3 standard deviations of our mean mu. So now that 95% in the empirical rule is an approximate value. We can use our calculators to find that 95% of the possible X values fall within actually 1.96 standard deviations of the mean mu. Let's figure out how we would actually do that. So if I want 95% in the middle, that would be 0.95 in the middle. And 1 minus 0.95 equals 0.05. And if I divide that by 2, I get 0.025. So I have 0.95 in the middle and 0.025 in each tail, which is just important if you have an old calculator that won't give you areas in the middle. We're going to do an inverse normal function to try and find out what z value gives me 0.95 in the middle. So I could do a left area of 0.025 will give me right here, or I could do center of 0.95 and it should give me from here to here. So I'm going to do second distribution. I'm going to do an inverse normal function. My area, if I want to do the left, would be 0.025. This is a standard normal. With the mu equals 0, mean equals 0, and standard deviation equals 1. If we want to find a z, because that's how z always tells us how many standard deviation. So z tells us how many standard deviations, so we'll use a standard normal, mu equals 0 and 1. So our mean will be 0, standard deviation of 1, the tail left, and so I get here that this is negative 1.96, which means this value is positive 1.96. And if I wanted to do the center instead, I would do 0.9 in the center. And it gives me negative, oh, sorry, I did 0.9, I was supposed to do 0.95. If I do 0.95 in the center, it tells me it goes from negative 1.96 to 1.96. So either way, we get this 1.96. So if X bar is going to be within 1.96 standard deviations for X bar of mu, then we could say that mu is within 1.96 standard deviations of X bar. Let's see, or summarize this then. So to summarize, we have a 95% probability that the sample mean X bar will be such that our interval, X bar plus or minus 1.96 sigma for X bar, contains our population mean mu, because here we say mu is within 1.96 standard deviations of X bar. So this means before we randomly select the sample, there is a 95% probability that we will obtain this specific interval that contains the population mean mu. So in other words, 95% of all the intervals that we might obtain if we took many, many intervals, because every single sample gives us a different result. So 95% of all the intervals we could have taken would contain our population mean mu. And that means then that 100% minus 95% or 5% of these intervals do not contain mu. This is why we call the interval x bar plus or minus 1.96 times the standard deviation for x bar a 95% confidence interval for our population mean. So back to our MBA example, we did take a sample now of n equals 10 and found x bar equals 79. Someone told us again that our standard deviation is 3.62 and that our data is normal. So let's find our 95% confidence interval for our population mean height. So up above we found our formula. We said our confidence interval will be x bar plus or minus 1.96 times the standard deviation for x bar. Let's see, so that would be x bar plus or minus 1.96, and the standard deviation of x bar I could replace with standard deviation of sigma over square root of n. Let's see, so x bar was 79 plus or minus 1.96. Our standard deviation is 3.62 over the square root of n, so square root of 10. I think we actually already calculated that up above, but I forgot what it was. So we have 79 plus or minus 2.24. Now, if you don't know what plus or minus means, it means we're going to do 79 minus 2.24. So 79 minus 2.24 gives me 76.76. And if I do 79 plus 2.24, I get 81.24. So it means you do 1 minus and you do 1 plus. So this is my confidence interval. And you'll get tired of writing this, but we're going to write it out every single time because the most important thing about statistics is knowing how to interpret the results, because calculators can give you results, but they can't interpret it for you. So we'd say something like, we are 95% confident that the population mean height for all the NBA players is between 76.76 and 81.24. So we're 95% confident that our population mean mu is between those two numbers. And that sounds a little bit better than saying, oh, our best estimate is just this 79 inches, when we realize it's probably not going to be exactly 79 inches. But the problem is, because we don't know our true value of our population mean mu, we don't know for sure whether or not mu is actually in our interval. But we are 95% confident that it's in the interval. By this we mean that we hope that our interval, which we just found from 76.76 to 81.24, we hope that that interval is one of the 95% of all the possible intervals that actually contains mu, and not one of the 5% of the intervals that does not contain mu. We say that the 95% is the confidence level associated with the confidence interval. This confidence level is a percentage that somehow expresses how confident we are that the confidence interval actually contains the population mean. So we are 95% confident that our population mean height is between 76.76 and 81.24. In this case, I actually have the data set with the heights of all the players. It's not very often that you have all the data from the population, but I do in this situation. And I found the population mean height is 79.14 inches. So did our confidence interval actually contain our population mean mu? Well, 79 is between 76 and 81, so yes, mu equals 79.14 is in between 76.76 and 81.24. So in this case, we were lucky. The confidence interval that I found was one of those 95% of all the possible intervals that actually contained mu. Now, because I actually have the data set for all the players, I can take a different sample and find a 95% confidence interval many times. I put my results from the first 20 samples in a table. So you can see this table. Each sample, I put the sample mean and the confidence interval that I would calculate from that sample mean. And then I also did a graph for the first next 100 results. Okay. So let's look at this. Better zoom out a little bit. So for this confidence interval, 77.5 to 81.9, does it contain my population mean mu, which is 79.14? So it would be between 79 and 81, so yes. My next one, yes, it would be in there. Yes, yes. Oh, but this one, notice my sample mean was really low this time. And so my confidence interval goes from 74 to 78. And so mu is actually not in there. So this one is a big no. Okay, then let's see. Yes, 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 yes. So again, I'm going through each interval and seeing if it contains my population mean mu of 79.14. Yes, 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 yes. And looks like all the rest are yes. So out of 20 confidence intervals, 19 of them contain my population mean mu, and only one did not. So out of 20, 19 contained mu. And guess what? That is 19 out of 20 is 95%. And we did a 95% confidence interval. So that's what a 95% confidence interval means. It means there were lots of different samples I could have taken. Each one would give me a different confidence interval, and 95% of them will actually contain my population mean mu. Now in practice, you only take one sample. Is there any way to know for sure whether it's a yes interval or a no interval? No, there's not, which is very unfortunate. But we hope we have pretty good odds that it will be one of the confidence intervals that actually contains our population mean mu. So here's this other graph where I did 100 confidence intervals. I drew a sketch here of our original population. You can see how it's pretty wide. Actually, scratch that. I just realized my scale was off. And I think I realized that before, but I didn't actually update it. So we'll ignore that part, but we can still look at our confidence intervals because that's still correct. So you can see here my population mean mu of our 79.14 is this line right here. And then you can see each black line represents a confidence interval. So each of the black lines is a confidence interval that contain our population mean mu. Notice our black lines are shifting quite a bit because each confidence interval from each different sample is quite a bit different. So some are over to the left more, some are to the right more. Every once in a while, you happen to get one, like here, 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 and here. The red lines, that they were shifted so far over that they actually missed our population mean mu. So, out of 100 confidence intervals, only 5 didn't contain mu. So that means 95% of them did. Oh, and I forgot I had the questions here. So did all of the confidence intervals actually contain our population mean mu of 79.14? No. How many of them actually contained it? Well, 95% did, because we were finding 95% confidence intervals. Now there's another applet here that we can go and explore just to reinforce this idea. There's different things here. We're dealing with means. We'll pick means. And it's a Z confidence interval. We haven't talked about the others yet, but that's what it is. I can set my mean mu for 29.14. Sorry, 79.14. And we know our standard deviation is 3.62. And we can find some confidence intervals. Oh, and n with 10. So I could take one confidence interval, or one sample. So notice these little blue dots are actual values in our sample. And I put a green dot for our sample mean that we picked. Notice here this line represents our population mean mu of 79.14. It did a green confidence interval with a little dot there for the actual sample mean. So this one contained our population mean mu. I could take another sample. Notice my values changed, my sample mean changed, and I got a different interval. If I do it again, I got different values, a different sample mean, and a different confidence interval. And I can just keep trying this. Different values, different sample mean, different confidence interval. Let's try doing 100 intervals. Okay, you can see these down here. All of these green spots are different sample means that we got. The red are the sample means that gave us a confidence interval that didn't actually contain our population mean mu. And out of this 100, you can see there's 1, 2, 3, 4, 5 confidence intervals where the mean was either so low or so high that our confidence interval doesn't contain our population mean mu. I could try again. This time, there were 4, so we're at 96%. When we say 95%, this is if we did infinitely many. So at just 100, we'll just be close to 95. So notice every time, again, I get different samples, values, which gives me a different sample mean, which gives me a different confidence interval. But overall, 95% of our confidence intervals should actually contain our population mean mu. 5% of them will not. When you take a sample and pick a confidence interval, there's no way to know if it's one of the good confidence intervals that contain mean mu or whether it's not.